Hey there and welcome to this video. In the following we'll be doing a paper implementation of the VQ-GAN model. With this paper you will be able to generate new beautiful looking images of a given dataset. For example, the authors trained on the Flickr landscape dataset and were able to generate these realistic looking images. These are not only really accurate to what you could find in real nature, but with this method you can also generate much bigger image sizes than you normally trained on. And for this video we will be using the Oxford flowers dataset, which consists of about 8,000 images of flowers, and our goal is to generate new flowers. For up, I would highly recommend you understanding the theory behind VQ-GAN, because I will not go over this in much detail in this video. So check out my explanation video, which is linked down below if you haven't already. Okay, so let's go over to the code. Okay, let's start with the encoder and the decoder. Both of the models have a lot of modules in common, and we will thus create a helper.py file where we will code all these shared modules. So we start off by importing all the torch modules. And the first module that we will need is a group norm. So this is the first module that we will need, and another one that is being used quite often is the swish activation. And this is just an alternative to the ReLU activation, and it shows some small empirical improvements. So having these basic modules established, we can now go to the next module, which is gonna be a ResNet block, which is heavily used by the encoder and the decoder. So this is going to be the residual block. It is taking in the number of input channels and the number of output channels. Then it is defining the block to be a torch sequential, and this consists of a group norm and the swish we have defined above. And then it's going to use a convolution with a kernel size of 1, a stride of 1 and a padding of 1, and then all of this repeated once again, the group norm, the swish and the 2D convolution. Then also what we are going to add is a channel up. This is just securing that the skip connection will work, because if we have different input and output channels, the skip connection will crash since both elements are not the same. So we simply define a channel up, and you can see how this is being used down here. We have the input channels. If they are not equal to the output channels, then we will first channel up basically our input and then use this as our skip connections and add this to our block that is defined up here. And if both the input channels and output channels are the same, we simply have the normal skip connection where we add the normal inputs to our block. Next up, we will be coding a class for a downsample block and an upsample block, which are being used by the encoder and the decoder respectively. The upsample block is using a single convolutional layer with an additional prescaling of the input features. This results in an output which is double the size of the input. For that it makes use of Torch's interpolation function, which takes in the feature and the scaling factor and will simply double both the height and width and fill in the new spots by their nearest neighbors. You can see an example here where I defined an input tensor and applied the interpolation, and the result is a tensor twice as big and having the blanks filled in. So now let's define the downsample block. As you can see, it's just the reverse of the upsample block, in which it is cutting the size of the tensor by half. First, a padding is added to both the height and width of the input tensor, and then the downsampling magic happens through the convolution, which has a stride of 2. Again, here's an example how the padding works by inserting one new row and one new column and filling it with zeros. This is done because else we would get a tensor which is not exactly half the size of the original one, but is off by 1. Okay, for the next part we will be coding the non-local blocks, and as I already mentioned in the explanation video, this is just sort of an attention mechanism just with pure convolutions. And again, I will link the paper down below so you can check it out if you're interested. So we have now defined all the layers that we're going to use. You can see that it is almost the same as the normal attention. We have the Q, the K and the V linear transformation, and additionally we also have a group norm and we have a projection for the last part. So let's define the forward pass. So first we normalize the inputs by our group norm, and then we just transform our inputs into the Q, K and V matrices. So and now we will do some reshaping so that the dimensions for the matrix multiplications will match. So that's basically just a reshape, and you will see in a second how this is important for the matrix multiplication. And what we're doing here is simply the normal attention. First, multiplying the Q and the K matrix together by using Torch's batch matrix multiplication. And then we simply scale by the square root of the channels, as also done in the normal attention mechanism. And then we apply the softmax to get a probability distribution. And then again some permutations so that the sizes match for the upcoming value multiplication. And here we construct the A matrix, so we attend to the important things by using again Torch batch matrix multiplication, and then we again reshape to bring it in the original shape back again. And then what is also different to a normal attention layer, we again make use of a skip connection. So yeah, and that's it for the non-local block. And as you see, it is simply an attention mechanism based on convolutions. And these are already all the submodules which we will be using in the encoder and the decoder, so we can now go over to coding them. Okay, so we will be starting by coding the encoder, and first of all we import all the necessary stuff. And now we import all the modules which we just coded in the helper.py file. Okay, so now let's define the encoder class. Okay, so first we define the channels, and the channels is just a list of all the different channel sizes which we will be using. So we start off with an image with 3 channels, and we scale it by the residual blocks to 128 and 128 and so on until we finally arrive at 512. Then the attention resolutions, since we're downscaling, we are decreasing the resolution size, and at this resolution we will imply another non-local block. And the number of resonant blocks simply tells us how many resonant blocks we want to put in at each stage. So this is also a measure of how big our encoder model will get. The resolution is a measure of how big our images are. Okay, so now let's define all the other layers. Okay, so this code is simply appending to our layers all the necessary things. So we go over all the channels, and then we always add the number of resonant blocks which we want to add. In our case, we defined it to 2. So for each channel size, we append 2 residual blocks, and then we check if the current resolution is in our attention resolutions. And since we only have like 1 element in it, then we append only at the resolution of 16 a non-local block. And then for each iteration except the last 2, we append a downsample block and decrease the resolution by half. Okay, so these were the M residual blocks and downsample blocks, and now we can append the rest of the blocks which are shown here. And now we added a resonant block, a non-local block, another resonant block, a group normal switch, and then an output convolutions which maps to our latent dimension. And then we construct the model down here by putting everything in a sequential. And then in the forward method, we simply call our model and put our inputs through. Okay, so yeah, that's already all there is to say about the encoder. And now we can switch to coding the decoder. And once again, importing everything we need for the decoder. Now let's define the decoder class. And if you're wondering what args is, it is basically just all the necessary arguments which we will later provide by Python's argument parser. And as already mentioned in the explanation video, the decoder is simply the reverse of the encoder. However, it is quite bigger than the encoder. We again define our channels, our attention resolutions, so the resolution where we will put in another non-local block, then the number of resonant blocks, as you already see, it's 3 instead of 2, so that's where the bigger size comes from. And we define our resolutions, and you can see we start by 16 by 16 images, and that is also the image size that the encoder is encoding images into. Okay, so now let's define our layers. So these are the first 4 layers our decoder consists of, and now let's define all the other layers. So again, this is pretty similar to the encoder, and using the loop we append the main layers to our layers list, and now we simply append the rest of the 3 modules to our layers. And the forward pass is simply just again calling our model. So the next part which we will be coding is the codebook, which is used for the vector quantization. And as usual, we start off with the normal imports. So now let's define the torch class. And again, this takes in our arguments. Here we simply define the number of codebook vectors which we want to have, and then also the latent dimension of these codebook vectors, and we define beta, and beta is a weighting factor for the codebook loss, as you will see in a minute. So here we define the essential thing of the codebook, which is the embedding matrix, and also additionally we initialize the weights by a uniform distribution. Okay, so that's already everything for the initialization. Now we can go to the forward pass of the codebook. So here we prepare the latent vectors for finding the minimal distance to the codebook vectors, and we simply do this by putting the channels as our last dimension and then flatten the latent vectors. Next up, we can now calculate the distances to the codebook vectors. And if this formula looks like gibberish to you and you're totally overwhelmed, don't worry, this is basically just the expanded version of the L2 loss. So you can pause the video now and actually see for yourself that it's really nothing more than just the expanded version, where we have the first term squared, the second one squared, both of these added, and then simply subtract twice the multiplication of the first element by the second element. And now we have the distances between all the latent vectors and all the embedding vectors, and now we can find out which ones are the closest. And now we need the indices of the embedding vectors to each of the latent vectors. And we do this by simply using Torch's argmin function, passing our distances in and looking along the first axis for finding the closest vectors. And now having the indices, we can now get the actual codebook vectors from our embedding matrix. And then we additionally reshape them to bring them back to our original shape Z. And now for the next part, we need to construct the codebook loss. And you may recognize that this is already the part where we imply the stop gradient function, which is called in Torch the detach function. So in the first part, we removed the quantized latent vectors from the gradient flow and then subtracting it from the original latent vectors, squaring it, and then for the second part, and you see how beta is being used here as a weighting factor. And this is now simply the opposite, where we now detach the original latent vectors and subtract it also again from the quantized ones and getting a distance measure by that. And yeah, don't be confused by this part. This is simply for preserving the gradients for the backward flow. And then finally we have to switch the axis again, and we move the channel axis for coming after the batch axis now, so that it has the original shape as our inputs. And then we are returning our quantized latent vectors, the indices of these codebook vectors, and our loss. And if you're wondering why we are also returning the indices, they will be used later in the transformer part. Okay, so having the codebook ready too, and the encoder and the decoder, we got now every module that we need for building the VQ-GAN. So again, let's start with the usual imports. And furthermore, we will also import the encoder, the decoder, and the codebook. So now let's define the VQ-GAN class. The arguments we take in will be again just the args, which is the arg parser. And now let's define the encoder, the decoder, and the codebook to be a submodule of the VQ-GAN. And moreover, we will also put the encoder, the decoder, and the codebook to the specified device. And the original VQ-GAN is also making use of a pre-quantization convolutional layer and a post-quantization convolutional layer. And they are just normal convolutional layers which will be applied before the quantization and after the quantization. And you will see in a second how this is exactly done. So now let's define the forward pass. Okay, first of all, we just encode the images using the encoder. Then we apply the pre-quantization convolution. And then we quantize the encoded images and get back the codebook mapping, the indices, and the codebook loss. And for the last part, we try to reconstruct the images by using the decoder. And finally, we return the decoded images, the indices, and the codebook loss. So essentially this would already be all there is to code. However, we will now be adding two more functions, one for encoding and one for decoding. They will be later used by the transformer separately, and this will make our lives way easier. So what that is, it is essentially just a forward method split up in two separate functions. For one, the encoding of an image, and the second for the decoding of an image. And if you saw the explanation video, you know that the authors used a variable lambda as a weighting factor between the VQ-VAE loss and the GAN loss. So let's write a function for calculating lambda. So if you take a look at the calculation of lambda again, you see that we are taking a ratio. G stands for the decoder and L resembles the last layer of the decoder. So this notation means to take the gradient with respect to the last layer of the decoder for both the perceptual loss and the GAN loss. In the code you see that we are first grabbing the last layer and then its corresponding weight. After that we are calculating the gradient using Torch's autograd function for both the perceptual reconstruction loss and the GAN loss with respect to the last layer. Retain graph means that we want to keep the current computational graph, which is just important that the backward pass can function properly. Now we take as described in the formula the ratio between both gradients and clipping the values to be between 0 and 10,000 and then returning lambda. One more thing that the authors suggested is to start the discriminator later in training. This ensures that the training doesn't fail to converge. That way the generator has time to learn already something about reconstructing images before the discriminator joins, who would otherwise have an easy time predicting which images are real and fake if it joins right from the start. The discriminator factor is an additional weight by which we will weight the discriminator. However, for this video we will just set it to 1, but feel free to try different values or even schedules. And we will write one more function which is also being used later by the transformer part, and that is a function for loading the checkpoint for the VQ-GAN. Okay, yeah, then for the next part we have the discriminator, and I will not be coding this right here because it is just taken from the official CycleGAN and Pix2Pix paper, so you can check out the link up here, and I also simplified quite a lot of the code. If it still looks really unreadable, have a look at this screenshot here. This is just basically what the init method is constructing. You see that we have this architecture which consists only of convolutions, leaky values and batch norms. And I also said in the explanation video that we are predicting each patch, and here's an example of what the output will look like if we feed in an image. And as you can see, we are getting back a 30 by 30 matrix which resembles each patch being real or fake. Okay, so yeah, for the next part we are going to look at the perceptual loss, which is gonna be the LPIPS. Sorry if I mispronounced that. And yeah, out of time reasons, I'm also just gonna show the code right here because it is also just taken from the authors. And for the overall understanding of the VQ-GAN, it is not that important. But anyways, we are going to start off by downloading the model, which is provided by the authors. And then here's the main class, the LPIPS, where we're going to make use of the VGG16, which is defined down here. And this is also loading a pre-trained model from the Torch vision module. And basically the only thing that is important for us is the forward pass of the LPIPS. You can see that we will feed both the real and the fake images through the VGG, and first applying a scaling layer, which you can see down here is just a normalization, and then we are taking the differences between each of the different feature channels, and eventually we're just going to take the average and returning this. And the way we are going to use it is shown here by constructing random real and fake images and then applying the loss onto it, and you can see we're getting back a scalar, which is a representation of how similar the images are. Okay, so now we are almost set for actually writing the training code. However, there's one more thing which we have to add, and I'm also just going to show this right here. And this is a utils file of different classes and methods which we are going to use throughout the video. And we start off by our data set, and this is just a class for how we are going to load the data that we are going, and specifically loading the Oxford Flowers data set. And you can see that we're inheriting from dataset, so we are constructing a Torch dataset, and for that we need at least two methods. That is, first of all, the length method, which is gonna return, as the name suggests, the length of our dataset, and then the get item. And get item will take in an index and will return an image. And you can see that we're applying a preprocess function on it, and this is just opening the image, converting it to RGB if it's not already. Then we are putting it into a NumPy array and applying our preprocessor, and the preprocessor is simply a rescaler, so if the sizes don't match, we will bring it to the desired sizes that we want, and we are also applying center crops. So after applying this preprocessing to the image, we will scale the image to be between -1 and 1, and then also transposing the channels, because the normal pillow library will load images and put the channel dimensions to be the last one. However, Torch wants it to be the first one, so that's why we are applying the transpose, and then we are simply returning the image. And down here you see we are actually loading the data. So we first constructing the image paths method, which I just showed up here, which takes in the dataset path, which is provided by our argument parser. And then the size, I already set it to 256 because that's the size we will be dealing with. And then we are constructing the data loader, which takes in our training data, our batch size, and we say that we do not want to shuffle the data. However, feel free to set this to true if you want to play around. And then down here we will define two more methods, and and you will see in a minute where they will be used, which is going to be an initialization for weights, for convolutional layers and for batch norms, and then down here a plot images function, which we will be using in the transformer stage for plotting basically reconstructions, new samples, and so on. And now finally we will be coding the actual training loop for the VQ-GAN. And as usual, I will start off by importing all the necessary modules. As you see, we have our perceptual loss, the VQ-GAN, then the aforementioned utilization functions for the data loading and the weight initialization, then the discriminator, and then other standard modules, for example, the argument parser. Okay, so now let's define the training class. And here you can see how we are using the weights initialization function, and they are going to be used for the discriminator. Now we are going to define the perceptual loss, and the last thing we are going to need is to define the optimizers for the training. And we will be going to write this function in a second. However, before that, we are also going to call a prepared training function, which will just set up all the directories for us. And then finally, when all of these things are done, we can actually call our training function. And also one more thing we're going to take off in here, we're going to push all the models to the desired device. Okay, so now first of all, let's define the configure optimizers function. Okay, so what we're doing is pretty simple. We are just going to construct two optimizers, and we're going to be using Adam. And for the first optimizer, for the VQ-VAE part, we're just going to get the encoder parameters, the decoder, the codebook, and from the two pre and post quantization convolutions, all the parameters, and bring them all into one big list, and then feeding these parameters to the Adam optimizer. And for the discriminator optimizer, we are also going to be using Adam, and same here, we're going to get the parameters of the discriminator and the learning rate, and the beta arguments will be later defined in the argument parser. And then we are returning both optimizers. So next up, let's define the prepared training function. And the prepared training function in our case will be as simple as creating two directories, one for the results where we will be logging images to, and then one for checkpoint where we will be saving the models to. Okay, and last but not least, we are finally going to write the training function. First of all, we are going to load the data. And here we're going to call the load data function, which we have defined in our utils file. Next, we're going to assign a variable to the number of batches we will have in one epoch. And now we're going to write the loop. For that, we're going to iterate over all the epochs. Here we are just using TQDM for better visualizations of the training process. And now we're going to iterate over all the batches. Since we're training this with a GPU, we will first bring all the images to the proper device. Next, we are going to call our VQ-GAN model and get back the reconstructions of the images and the codebook loss. Next, we will be sending both the real and the reconstructed images through the discriminator. And remember, we wrote a function for a discriminator factor, meaning that we want to start the discriminator later in training. We're now going to calculate the discriminator factor. And you see that the threshold will be an argument, which we will also provide in the argument parser, which will indicate when to start the discriminator. Next up, we will be calculating the perceptual and the reconstruction loss. And maybe one thing to note is that we are not going to use the L2 loss for the reconstruction loss. We are going to use the L1 loss, meaning we only take the absolute difference between both the images and the decoded images. Here we are just going to fuse them together and take the mean value. And the G-loss will be the discriminator loss for our generator. Now it's time to calculate lambda. And now finally we can calculate the VQ loss. And you can also see how the discriminator factor is being used here, as to that the discriminator loss will not be taken into account until that we have passed the discriminator star threshold. And now here comes the second part for the hinge loss, which is going to affect the discriminator. And if you're confused where the formulas for both of these terms and the G-loss are coming from, this is just a hinge loss which is inspired by support vector machines. And you can see a screenshot of the loss here, and I will also link some resources in the description where you can learn more. And in this line we're adding the real and fake discriminator loss and also weighting it by the discriminator factor. And now it's time for the backward pass. First we will zero grade both optimizers and backward the loss. And now we're going to do the weight update. And also make sure to do all the last steps in this order, because else you will get some really annoying errors where I spent a lot of time solving these. And now we're going to write some code for logging images, logging both losses to TQDM, and making sure we are saving the VQ-GAN after each epoch. And yeah, that's it. That's all that we need for the VQ-GAN training. And now finally, let me just define all the arguments that we are going to need for the training. Okay, as you see, I've now defined all the arguments, and they consist first of all of the latent dimension, of the image sizes, of the number of codebook vectors. We will be using 1024. Then the beta, which is the weighting factor in the codebook loss. Then image channels, we will be using RGB images, so it's going to be 3. Then I define a dataset path, then the device to be default for CUDA, so GPU training. Then I will use a batch size of 6. I will be doing 50 epochs. This is going to be the base learning rate. Here both beta 1 and beta 2 for the Adam optimizer. Then we're going to start the discriminator after 10,000 steps. And then, as I already mentioned before, the discriminator factor will be equal to 1. And 2 more weighting factors, one for the reconstruction loss and one for the perceptual loss, will also be initialized with 1. Then I set the specific path for my dataset where the Oxford flowers are located. And then I'm going to call our training class. And I also want to mention one more thing, is that my code is heavily oriented on the structure of the original implementation. So if there's anything which is unclear, make sure to check out the original implementation, which I also linked down below. So the model has now been training for about 50 epochs, and you can see the results here. On top you see the original images, and below that you always see the reconstruction for each image. And as I go through here, you can see that the method is working, that it sort of reconstructs. It gets the shape pretty good, I would say, but it still is a pretty unsharp, and also sometimes the colors are a bit off. And you see this weird sort of pattern which goes over the whole image. I'm not quite sure where this is coming from, but I am quite sure that if you let this model train for even longer, that you will at some point get to the results, which the paper also has showcased, because I just trained it for 50 epochs. But feel free to try it out even longer and maybe try even other hyperparameters, for example the learning rate or any other hyperparameter. And maybe just a quick side note, if anyone's interested, I trained this on my own machine, an RTX 3090, and it took the GPU about 12 hours for about 50 epochs with a batch size of 6. And I will also upload the checkpoint from the last epoch that I trained it on, so you can try it out yourself for the flowers dataset and see yourself, so that you don't have to train it on your own. So after having the first stage of the VQ-GAN trained, we can now take care of the second stage. So the basic idea behind this stage is that we encode images to their codebook vectors and then replace some of these vectors randomly, and then have a transformer for finding the wrong codebook vectors and have them replaced. So we need some transformer architecture, and the authors decided to go with a GPT-like architecture, and specifically MinGPT. Since this video is more focused on the usage of the transformer instead of how the transformer is constructed, I will just briefly go over the code here. So, and this is the code. As you can see, we have the main class, the GPT class here, and it is really just a transformer architecture. You see that we have the token embeddings here, which is an embedding matrix, and then we have a positional embedding, then the dropouts, and here comes the real transformer part, which is defined in the blocks up here. And also just here you can see that we have self-attention and the MLP on top, so really just a basic procedure of a transformer. And then we have a decoder head, which consists of a layer norm and a linear layer, and you can see that the output size will be the same as our vocabulary size, in our case 1024. And furthermore, down here we have some weight initializations, and then down here you can see the actual forward method where we first encode the tokens, and then down here get our positions embeddings and then add them together, apply the dropout, and then feed them through all the blocks and apply the layer norm, and then finally we get the predictions by feeding it through the prediction head and then returning the predictions. So yeah, that's essentially the whole transformer class which we will be using, and now we can go over to actually coding our VQ-GAN transformer part. So let's get into the code and start by importing all the modules and defining the transformer class. Also a quick note, in this video I will only be considering the unconditional case for the second stage and not the conditional for time reasons. However, it is fairly straightforward for bringing the current code to the conditional case with which you could train to generate class specific images. First of all, we will be defining a start of sentence token so that the transformer always has a valid token to start from. Next, we load the VQ-GAN model using a function we will create in a second and define the transformer config and initialize the transformer. And the last variable we need will be the ratio of tokens we keep and don't replace by random tokens. This also acts as a hyperparameter and you can feel free to tune it as you want. Now let's define the function for loading VQ-GAN, which also sets it in evaluation mode. We will need a couple of helper functions which we will define now. First of all, a method for encoding an image to the codebook vectors with an additional flattening of the tokens since the transformer expects a flat sequence. Next up, the reverse of the encoding method, which takes in the indices of the codebook vectors and then returns the image as a numpy array. Specifically, we will be calling the embedding matrix of the codebook with the indices and retrieve the matching latent vectors. Then we reshape the tensor and move the channel dimensions to be after the batch dimension, and finally calling the decode method for our VQ-GAN. This method will be later used for plotting images. Now we can define the forward pass for the second stage. We will take in a batch of images and first encode it to their corresponding quantized latent vectors. However, we will only consider the codebook indices since that is what the transformer takes in. After that, we will define a tensor which contains the SOS tokens, which we will later insert at the beginning of each element in the batch. Now we can take care of replacing random indices by other random indices. This is done by first constructing a mask where each element will be a 1 with a probability of p-keep. So if p-keep equals 0.5, then our mask consists of 50% zeros and 50% ones on average. Next, we sample random indices in the shape of our codebook indices and then create the new indices by leaving all indices untouched if the mask has a 1 at this position and take the random index if the position has a 0. Now we simply concatenate the SOS tokens to the beginning and feed the altered indices in the transformer, which is supposed to predict the original indices back. And finally, we are returning both the predictions and the original indices. So that's it for the basic model and its forward pass. In the following, I'll be creating a few more functions for actually sampling images from the transformer. First of all, a top k function. In general, this sort of function returns the k highest values in a tensor. PyTorch already provides such a function, however only returns the k elements and their indices, and we want to have a tensor which has the same dimension as the input and sets every element to some really small number and keeps the top k entries. And this is what our function will be doing. This will be important in the next function we are going to write, which is a method for sampling images. Let me first explain the idea. The transformer is autoregressive, meaning we are generating each token one at a time. So say we want to generate a completely new image. We start with the SOS token and feed it in. Then we let the model predict which token could be the next one. Now we have the SOS token and the first image token. Now we take both of these and feed it back in again and then end up with 3 tokens in total. We do this over and over until we have enough tokens. For our normal images we need 256 because our latent dimension is 16 by 16. So our steps would be equal to 256. And in detail, the method works by first setting our transformer in evaluation mode and prepend the SOS tokens, just as in the normal forward method. Now we iterate over the number of steps and feed the current image into the transformer and then only take the very last prediction and scale it by the temperature. Now we apply the top k function which we wrote earlier and convert the predictions into probabilities using a softmax. Finally, we sample the new token based on the probabilities and append it to the array of image tokens. And after all the image indices are generated, we cut off the SOS token, set the transformer back to training and return the image. Super simple, right? Oh, and one more thing. Remember that with VQ-GAN we can generate images much larger than we trained on, right? Now you can understand why. Because we don't generally have to stop after we have generated, for example, 256 tokens. We could just go further and generate 500 or even more. And since our decoder is fully convolutional, it doesn't care how many tokens it receives. So now for the final method for the VQ-GAN transformer, we just write a function which helps us investigate the quality of the model. The outcome of this method will be a dictionary which contains the normal image we fed in, the reconstruction of this image which isn't using the transformer, then the famous pictures where we cut off half of the image and let the transformer sample the bottom half, and then a completely new sampled image. And now this will be the last file which we have to code, and then we are ready with the whole VQ-GAN model. And as already said, this will include the training class for the VQ-GAN transformer. And as always, let's import all the stuff and define the class. So you see that we are defining the model to be the VQ-GAN transformer. Then we again need to write the configure optimizers, which will return the optimizer. And then we are calling the self.train, which will take care of the training loop. So this really long function is basically just serving one purpose, is that some modules are supposed to get weight decay and some modules are not. And in particular, all the modules which are in here, so all the linear modules, they are supposed to get the weight decay, and layer norms and embedding layers and also the positional embeddings, they are supposed to not receive weight decay. And this is essentially all that is happening in this function. And finally, we are constructing the AtomW optimizer and returning it. And after this really long method, we can now write the training loop. So until here, that's completely the same as the VQ-GAN training. We are first loading the training data set and then iterating over all the epochs, then again constructing the TQDM, which is just for the visual representation of our loss and the process of the training in general. And then we loop over our training data set and get the images out. Now we will put them to the proper device. And as you can see here, we are now calling our model, which takes in the images and returns the logits and the targets. We will be using cross entropy for calculating the loss. So this will be the loss, and now we can backward the loss and then calculate the weight update for the transformer. And now I will just write the code for updating the progress bar of TQDM. So that is the whole training loop, and now after each epoch we will sample some images and then save them to the disk and also plot the images and save the transformer checkpoint. And now we got the whole training loop for the transformer training set up, and for the final step I will be again creating the argument parser, creating all the arguments and then calling our training function. And as you can see, I just copied all the arguments from the VQ-GAN argument parser, and I simply added just these two things that we need. First of all, the probability for index keeping, which we were using in the transformer, and also the start of sentence token, which is also used in the transformer. Okay, so now I will start the training and I will come back when the training has finished and show you the results. So the training of the transformer has now been finished and you can see the results shown here. And I gotta say, you can recognize that these are flowers, but obviously it is not perfect. I've been training it for 100 epochs and the loss has still been going down, so I believe that training it for even longer will again result in better results. And again, you see here that this weird pattern appears again, and this clearly shows that the second stage is dependent on the first stage. If the first stage is not well trained, the second stage will also not magically create beautiful looking flowers. So I believe that this is a matter for better training the first stage, and then I'm sure that you will also get pretty nice results here. And again, just for the record, it took my computer about 8 hours to complete the 100 epochs. And just quickly, one more thing, if you're interested in running the code on your own, you can check out the GitHub repository where I uploaded all the files. So, and that's it with the implementation of the VQ-GAN model. I really hope you enjoyed it and let me know about things I can improve, since this one and the explanation video are basically my first videos on YouTube. And with that being said, I wish you a nice day.